do you mind if we video this? If it's okay with the speaker, we try to make a video archive of our different talks that we have.
And we put them on Facebook.
That's no problem at all.
Okay, great, thank you. Well, welcome everybody to, let's see, this is January 2018 and the virtual lecture series for the Big Bear Valley Astronomical Society. I'm going to keep this introduction very short tonight because I have almost no voice left from this cold Teresa and I came back from vacation with. This, can you say a few words?
We met Gerald at during the solar eclipse when we went up to Mitchell, Oregon. Mitchell, Oregon. We had gotten space there with the East Bay Astronomical Society, and we met Gerald and his wife and other members of the East Bay Astronomical Society, and we already knew a few people there, like Richard Ozer, but then we got to know many more people there, and we had a great time. And
I had known about Chabot Observatory since I was a child. I went there numerous times, dragged my mom to it very many times, so I've been hoping to get somebody to talk about the new Chabot Observatory. I know it's a completely different facility than I remember as a child. So in the same room, or same house we were staying in Mitchell, was Gerald, and I began twisting his arm immediately upon getting there to give a talk, so he finally agreed. Gerald McKeegan is going to speak this evening about the Near-Earth Object Follow-Up and Tracking Program that he runs through the Chabot Observatory Science Center, and I'm not getting that all quite, oh, it says right, Chabot Space and Science Center, I can read it. So please join me in welcoming Gerald McKeegan.
Well, thank you, everybody. You see on the slide there a photograph of the Chabot Space and Science Center. It shows our observatories. We actually have 3 observatories up there, various ages. The one in the small dome you see there is 135 years old now, and the one in the big dome there is 102 years old. And there's another one that's out of the frame off to the right there. That's our newest one. That's the 36-inch reflecting telescope. It's only 14 years old. So you get a variety of different telescopes up there. Plus we have a planetarium, we have a theater, we've got exhibit spaces and so on. It's in the hills above the city of Oakland. So if you're ever in the Bay Area and want to stop by and pay us a visit, you're more than welcome. Just a little background on me. I am on the board of directors of the Chabot Space and Science Center. I'm also on the board of directors of the East Bay Astronomical Society. I've worked in the aerospace industry for more than 40 years. I'm retired now. And one of the things I do for Chabot, in addition to operating the telescopes and doing planetarium shows, I also conduct the Near-Earth Object asteroid search program for Chabot using that new 36-inch telescope. So what I want to do is kind of talk to you a little bit about near-Earth objects and explain a little bit about them and how we go about finding them, and you throw in a few other facts while we're at it. So if I can have the next slide, please. So what is a near-Earth object? In order to be a near-Earth object, it's either an asteroid or a comet. Near-Earth objects are almost all asteroids. Maybe 95% of them are asteroids, and maybe 5% are comets, especially older comets that have sort of degraded and aren't outgassing anymore. To be considered a near-Earth object, they're orbiting the Sun in such a way that their orbits come within about 45 million kilometers of the Earth's orbit. It's about 28 million miles, and it's 0.3 astronomical units. And the reason for that distance is that's the distance between the Earth and the planet Venus and the two of them are closest to each other. So basically anything that gets closer to the Earth's orbit than the planet Venus is considered to be a very near-Earth object. Now I'm going to talk mostly about asteroids tonight, and there's a subcategory of near-Earth objects called near-Earth asteroids, which is what we'll talk about mostly tonight. And then there's also what we call PHA, or potentially hazardous asteroids, and this is a subclass of the near-Earth objects. Potentially hazardous asteroids are 140 meters or larger in size. There's also a distance requirement that I'm going to talk about in a few minutes here. So we'll get into that a little bit more in a couple minutes. Thus far, our search program, which is a global search program, has found 17,600, give or take a few, near-Earth objects. That's as of last week. But based on the distribution of the sizes and the quantities within each size bucket, we figure that there's at least 1 million more that we need to find yet, larger than 10 meters in size. And I'll show you a little graph in a little while that kind of illustrates that point. So near-Earth objects, if I can have the next slide, near-Earth objects, especially the near-Earth asteroids, come from the main asteroid belt. They have migrated from the main asteroid belt into an orbit that brings them close to or crosses the Earth's orbit. In fact, some of them actually orbit, the orbits have changed so much they're actually totally inside of the Earth's orbit. Most of you, I think, know that the main asteroid belt is between Mars and Jupiter. There's millions of objects out there, millions of asteroids, and occasionally one of them manages to get out of that orbit, nice stable orbit, and between Mars and Jupiter, and they get out of that orbit and wander in and get close to the Earth. So, there's three mechanisms by which they can get dislodged from the main asteroid belt. If I can have the next slide, please. Collisions. Now, the main asteroid belt, if you watch Discovery Channel or Science Channel, you'll notice that they're always showing the main asteroid belt as being this place where there's a swarm of asteroids. So many asteroids that if you were flying around out there, you'd be jinking and jiving trying to miss them all. That's not what it's like at all. In fact, the main asteroid belt is mostly a lot of nothing. It's millions of miles wide, millions of miles deep, and even though there are several million asteroids out in the main belt, you're flying around out there, you're not likely to see any of them. They're so far apart. But occasionally they do bump into each other, and when that happens, not only do they break up, but they can change their orbital parameters and cause them to go into elliptical orbits. Another way they get out of the main belt is through gravitational perturbations, and that's primarily from Jupiter. So if they get in just the right spot, Jupiter's strong gravity will tug on them and change the eccentricity of the orbit so that they wander in towards the inner part of the solar system. Another way they can migrate out of there is by a thermal perturbation called the Yarkovsky effect. I'm not sure if you folks are familiar with that. You can imagine an asteroid's out there floating around in the main asteroid belt. That asteroid is slowly rotating. As it does so, one side of it is heated by the sun. As that side rotates away from the sun, it now radiates heat out into space. That creates a small force on the asteroid. It's a very tiny force, but it's continuous. And over time, that slowly perturbs the orbit. So these are the three primary mechanisms for getting asteroids out of the main asteroid belt and getting them into orbits that come close to or across the Earth's orbit. A few facts about asteroids, if I can have the next slide, please. Near-Earth asteroids range in size from biggest, which is 34 kilometers in size, but there's only one of those, so all the rest are much smaller. They range down to a couple of meters in size, and as we go down in size, we go up in the number of asteroids in each size bucket. Now there's a little bit of debate about at what point does it stop being an asteroid and start being a meteoroid. Nobody has actually officially defined that yet. I know there's been some people trying to cut it off at 1 meter, so that anything smaller than 1 meter is considered a meteoroid. But basically, rocks, big enough to be seen from a distance, those are our asteroids, and they occasionally drop down through our atmosphere. We had one drop down, about a 2 meter one, drop down through the atmosphere just 2 days ago out in Michigan. And I understand, saw something today that some people are finding pieces of it. So most of the asteroids are small. We think that there are fewer than 1,000 of them that are larger than 1 kilometer. And 1 kilometer is kind of the cutoff level for when we worry about if there's an impact that's a global event, extinction level event. That's kind of an arbitrary limit, but that's what we've set. Congress has actually mandated that we fine all of the 1 kilometer or larger asteroids. Like I say, there's fewer than 1,000, probably around 900, 950 or so, and we've located more than 90% of them. So we know where they are, we're tracking them, and we can say with certainty that for at least the next couple hundred years, none of them are going to hit the Earth, so we can all relax. There are a lot more asteroids smaller than 1 kilometer. In fact, most of them are smaller than 1 kilometer. And in fact, most of them are smaller than 140 meters. And 140 meters is, I think I mentioned earlier, that's the lower size considered a potentially hazardous asteroid. The other thing, in order for it to be a potentially hazardous asteroid, it has to have a MOID distance of less than 0.05 astronomical units. And MOID is the minimum orbit intersect distance, which is the distance between the Earth's orbit and the asteroid orbit. If that distance is less than 0.05 and it's more than 140 meters, then it's considered a PHA. Now, notice that I said the Earth's orbit, not the Earth itself. An asteroid can have a MOID of 0, but never hit the Earth because the orbits of the Earth and the orbit of the asteroid are not synchronized in any way, and one is always someplace else when the other one gets at the intersection point. So, the thing we emphasize is not how close it gets to the Earth, how close it gets to the Earth's orbit. Okay, I want to talk a little bit about the structure of them and the composition. So next slide. They're not spherical. Again, you see a lot of stuff on TV showing them sort of spherical. They're actually very irregular in shape and very irregular in structure. Some of them are monolithic, like a solid rock. Can be solid iron or nickel. That turns out to be only a very small percentage of them. Most of them are just rock, silicate rock. And quite a few of them turn out to be not monolithic, but rather a rubble pile. So if you can imagine a big pile of gravel and stones taken out into space and just allowed to gravitationally attract each other, they become a rubble pile that looks like an asteroid. They break up very easily. There have been various attempts to classify asteroids. At one time we were just classifying based on how similar they were to different types of meteorites, like achondrite meteorite or L-chondrite, stone meteorite. several years ago, a graduate student named David Tholen developed a classification technique, and that's one of the techniques that we use now to classify asteroids. In fact, if you go to the next slide, please. You see a chart here of the Tholen classification system. It's got 14 different characteristics based on things like albedo, which is the surface reflectivity of the asteroid, color absorption, spectral reflectivity, and you see some of the criteria there in the chart. We still tend to refer to them also based on their relationship to meteorites, whether they're stones or irons or so on and so forth. So, how do we find them? Let's look at the next slide. There's some different techniques that we use, and I'm going to kind of talk to you in general about the general techniques that are used to find most asteroids, and then I'll talk more specifically about how we do it at Chabot Space and Science Center. So next slide. Almost all near-Earth object discoveries are made by professional survey telescopes. There are several of them around the world. This slide shows you a few of them. The Catalina Sky Survey is on Mount Lebanon outside of Tucson, Arizona. And they have 3 telescopes up there that search the sky almost every night when the weather is good. And there is also the Pan-STARRS 1 telescope, which is on Haleakala in Hawaii. In fact, Pan-STARRS 2 is supposed to come online here pretty soon. I think they were supposed to already be online, but I'm not sure what's going on there. Pan-STARRS 1 has been in operation for several years. These telescopes survey the sky every night whenever they can. They try to survey large parts of the sky, and if they spot a moving object, they check very quickly to see if it's a known object. If it's not, then they report that to an organization called the Minor Planet Center, which then asks for other observatories to try to confirm that. So, next slide, please. I'll show you a little map here. This is a Google map showing all or most of the observatories around the world that augment the survey telescopes. There are about 300 of these observatories, and they do the confirmation and follow-up work to kind of back up the survey telescope. So a survey telescope might spot an object, say, see it for maybe a 30-minute period of time, and then they move on to something else. These other telescopes then come in and they take additional observations over 2 hours or a few days and try to confirm the asteroid and try to get enough data so we can compute orbits. All of the data from all of these observatories is submitted to the International Astronomical Union's Minor Planet Center, which is in Cambridge, Massachusetts. The Minor Planet Center collects the data, they analyze it, they have several computers that they use that do automatically analyze all the data that comes in. They share their data with NASA, the Jet Propulsion Laboratory in Pasadena, and they compare incoming data to their database of known asteroids, also a database of known man-made objects, whether it's satellites or vehicles still floating around in space, and try to determine whether it's a known object. If not, then they ask the observatories around the world to continue to do observations until they're convinced that they've got an object and they know what it is, and they post a orbit and give it an official designation. So you've got the survey telescopes working, you've got all these auxiliary telescopes. By the way, I might mention, more than half of these auxiliary telescopes in this program are amateur telescopes. And there are quite a few amateurs out there who have put together some pretty sophisticated observatories, and they support this program as often as they can. There's a guy, for example, in England, his name is Pete Birtwistle. He has an observatory set up in his backyard, and I swear the guy never sleeps, or he sleeps on it at work instead of at night, because he is at it every single night, backing up the survey telescope. Okay, so how do these guys do finding all the asteroids? So we'll look at the next slide, please. This is a graph to give you kind of an idea of where we stand as of last year in terms of finding all the asteroids. And the red line is our best guess for how many asteroids should be out there, near-Earth asteroids in various sized buckets. And you notice that the scale on the left is logarithmic. So we expect to see literally millions of asteroids in the small size range, say the range of the Chelyabinsk object, which was about 17 to 19 meters in size. Excuse me. And you see that the brown lines there, that indicates how many we found in each category. You see that off to the right there, we have found all of the big ones, the ones larger than 1 kilometer in size, not all of them, but nearly all of them. But as you get into the smaller sizes, our inventory is pretty low compared to what we think is out there. I mentioned a while ago that Congress had tasked NASA back in the 1990s with finding 100% of the 1 kilometer or larger asteroids. In the early 2000s, there was an initial act of Congress, the George Brown Act, which said they should find 100 or 90% of the near-Earth objects larger than 140 meters, because those would be considered city busters. Asteroids that wouldn't cause global extinction or global catastrophes, but could cause a lot of problems on a very wide regional basis. So, as you can see, we're still quite a bit short of that goal. We were supposed to have accomplished it by the year 2020. Obviously, we're not going to make it. We've been doing this now since the mid-1990s, and we've got a long way to go yet before we set goal. Go to the next slide. I'll just talk a little bit about our program at Chabot. Our telescope is not a telescope that's good for wide area surveying. We have a 36-inch Cassegrain telescope, relatively narrow field of view. So rather than using it to just search the sky for asteroids, we use it for what we call confirmation and follow-up. Confirmation is confirming potential new discoveries by the survey telescopes or some other observatory where they've spotted an object, they've tracked it maybe for 30 minutes or so. Now they need other observatories to confirm its existence. So we do quite a bit of that. We also do a lot of follow-up, which is continuing observations over long periods of time. Once an asteroid is confirmed, Minor Planet Center assigns a designation to it. You go into a catalog, and if you don't follow up on it, pretty soon you don't know where it is anymore. So it's real essential that we have follow-up observations. I'll talk a little bit more about that here in a few minutes. The type of data that we look for when we are doing our program, if you go to the next slide, astrometry, which is position data. Um, we report the rate of ascension and declination of the object. We also report its brightness or luminosity. For us at Chabot, we look in the red part of the spectrum. Asteroids tend to be a little bit brighter in the red part of the spectrum. So that's what we use. Other observatories use different parts of the spectrum. So we're providing position data, and we're also providing precise timing data and the photometry, how bright the object is. And the photometry is used to estimate the size. We can't see the asteroid as a three-dimensional object. We just see it as a point of light, a starlight. In fact, for the asteroid, it means starlight. And so we just see a star that moves across the sky. But by looking at it, once we know its distance, by looking at its apparent brightness, we can make an estimate of the size.
Do you also look at the photometric curve to determine the rotation rate or anything like that?
We don't do that at Chabot. There are other observatories that do concentrate on light curves. That's not what we do at Chabot. We try to actually confirm or follow up on quite a few asteroids during a night's observing. Light curve work takes a long time. In the course of 6 hours of observing, we may do 8 or 10 asteroids at Chabot. Light curve folks, they're going to do maybe one asteroid in that period of time. So other observatories do the light curve work. We just do the astrometry and the photometry. Okay, if we go to the next slide, kind of go through the process here. We start out by taking 3 or 4 images of the same part of the sky. And these are FITS images. And I'm sure some of you guys who are sharp-eyed, you're looking and you can already spot the asteroid, right? And we stretch these images because we're looking for something that's quite often very faint. So we stretch them, make them look really ugly. And then we go through a little bit of processing. Now, when we do this, we know what part of the sky the telescope is pointed at, but what we need to be able to do is identify most or all of the stars in the field of view, because that's how we determine the scaling of these images. So when we process these, we compare it to a star catalog. We use UCAC4 at Chabot. In fact, we go to the next slide. We match it to the stars to that catalog. We use that information to plate solve the images, which is a way of developing an equation that matches pixel position to RA and declination. Once we've done that, then we blade through it, and we see a moving object. And if we can't see the moving object, then we look for the blue arrow. So you see the asteroid there. Once we have identified it, then we have to go through a process of extracting data from those individual images. So if we go to the next slide, you see the 4 images again, and I'm sure all of you had already spotted it. But there's the asteroid in each of those images. We use specialized software to extract data from each of the images. In the data that we get, you see there in the red outlined box. But our software gives us a lot of information. It helps us sort false alarms from the real thing, because we look at the point spread function, which you see up in the upper right-hand corner of that image there. If it's an asteroid, it should have a nice point spread function like a star would have. If it's an artifact, like a hot pixel or cosmic ray strike, it's going to look very different. Once we do this, You see there in the red box that we have the rate ascension, declination. You also see the time, and the time is real important. We have to be as precise as we can with time. And we all work in coordinated universal time. And it's real important that all of our computers, everything that we are using to get time information is accurate. So the computer we use at Chabot, every 15 minutes it goes out and rechecks the clock, makes sure that that clock is as accurate as possible. A lot of the observatories are now using GPS data to make sure that their clock is very accurate. There are some issues with that, though. What we do is we take a picture. The camera records the time at which the picture begins, and it records also how long the exposure is. The time we report in our image is, or our data, is the midpoint between the start and the end time of each image. So if we do a 30-second image, it's going to be the time halfway through that, which is 30 seconds. Problem you run into is, when does the image actually start? The camera typically records the time at which it sent the signal, or the computer sent the signal to the camera to open the shutter. But there is a small lag between that time and when the shutter is fully open. And that's becoming an issue now as we observe some asteroids that are very close and moving very fast. There are various techniques that some of the observatories are trying to use now to try to get even more accurate than they already are with the time. So once we have our data, we have to email it to the Minor Planet Center. So if we go to the next slide, you see a formatted email here. The emails have to be in text-only format. They're being sent directly to a computer. They're not being read by a human being unless there's something wrong with it. They're going directly to a computer, so the formatting of the email has to be real precise. We send it to the Minor Planet Center in Massachusetts. Emails are automatically processed within, literally sometimes within seconds. And Minor Planet Center will automatically respond back to us, letting us know they've received the observation report, letting us know how many of the observations they've used, and if there are any problems with any of the observations. Occasionally we run into things like the individual data points don't match a great circle, or there is some timing issue or something like that. So we get those responses from Minor Planet often within less than a minute. So you know, having those high-speed computers working on that really works out well for them. After the Minor Planet Center gets, for new discoveries, after the Minor Planet Center gets 2 to 3 nights worth of firming data from a number of different observatories, they issue what's called a Minor Planet Electronic Circular, or MPEC. And this is the document that officially assigns a designation to the asteroid. It's now part of our master catalog. The MPEC includes things like the orbital elements. It lists all of the confirming observations that were used to determine that it's a legitimate object, and it provides an ephemeris for the next few days in case anybody wants to go back and look at it again. Typical designation is something like 2018 AG3. 2018, of course, is the year of discovery. The letter A, that first letter, is a half-month designator. So A is the first half of January, B is the second half of January, C is the first half of February, and so forth. And then there's a letter number combination after that. It's merely the sequence of objects discovered during that half-month period. Now, once this has happened, the object is now an official cataloged asteroid, but we're not done. If all we did were these 2 or 3 nights worth of observations, the data would be just enough to give us an orbit that's accurate enough to tell you where it might be in a few days. But if you want to know where it's going to be in a few years, you don't have enough data yet. You don't have an accurate enough set of orbital elements. So it's real critical that we have follow-up observations. So go to the next slide. One of the reasons for this is that all these observations are done from the ground. Okay? So they're looking at night. So the asteroid is at opposition. The time window may be very short. And like I say, the initial orbit determination can have a high degree of uncertainty. And over time, as we get farther and farther away from those initial observations, the uncertainty increases. Just as a point of reference, because we don't get enough follow-up observations sometimes, asteroids can be lost. And more than half the asteroids on the potentially hazardous asteroid list are lost. We don't know where they are anymore. We knew where they were when they were discovered and a short time afterwards, but there was not enough follow-up observations, so we're not so sure where they are right now. And those are the ones that we worry about the most. In particular, for potential impactors, it's critical that we get follow-up observations, especially if we're predicting, say, an impact or possibility of an impact at some future date. And as we get follow-up observations, it's possible that initially those observations cause the probability of impact to increase. Then over time, more observations, the probability goes down and may actually be eliminated. So I'm going to try to illustrate that point here by kind of doing a hypothetical, very extreme example of a potential future close approach of an asteroid that may have a probability of a impact. So if we go to the next slide, this is an example, like I said, it's an extreme example. Let's say we've observed an asteroid over a period of about 48 hours. We've collected 21 observations. Minor Planet says, Planet Center issues an MPEC saying, okay, we're given this official designation, it's cataloged. And then looking 28 months from now, it appears that this asteroid is going to pass very close to the Earth. But based on the very limited data that we have at this point, we have a very wide uncertainty region. And the Earth is within that uncertainty region. So even though the nominal, the crosshairs that you see in that image there, even though the nominal flyby distance is quite a ways away from the Earth, because the Earth is inside the uncertainty region, we say it has some impact probability. I've given it just arbitrarily 1.16%. So what this says, we're predicting at this point, it's 2 days into observing this asteroid, we're predicting that 28 months from now, this asteroid is going to pass very close to the Earth, and there's a 1.16% probability that it's going to impact the Earth. So we do some follow-up. So for the next few days, we do some more follow-up. Next image. And now, after about 5 days, we've collected a total of 72 observations. That allows us to constrain the uncertainty region. It's now smaller. we're still predicting the nominal flyby distance is a very safe distance away from the Earth. The uncertainty region is smaller, but the Earth is still in that uncertainty region. And because of that, our impact probability has actually gone up. So now it's up to a little over 2%. So that might be a little concerning, especially since after this 5-day period, you're not able to observe it anymore. So it actually got too close to the nighttime or daytime side, and we can't see it anymore. So we're going to have to spend some time just wondering what's happening. So about a year later, next slide, after 13 months, we're again able to observe it, or collect a few more observations. We now have a total of 84 observations. And as you can see, that has constrained the uncertainty even more. We're still predicting the nominal position at flyby is quite a ways away from the Earth, but a little bit of the Earth is still in that uncertainty region. So our probability is not yet zero, it's still about 0.22%. So once again, we lose it. It goes into the sunrise or sunset, and we can't see it anymore. And 27 months after its initial discovery, and only a month before the predicted flyby, we're again able to observe it. We collect about 105 observations, and we now are able to constrain the uncertainty to a very small region, and the impact probability is now zero because the Earth is no longer in the uncertainty region. Now you notice that our nominal flyby location has always stayed pretty much in the same position. What's happened is, as we collect more and more follow-up observations, the uncertainty zone shrinks, and eventually the Earth is no longer in that uncertainty zone. That's why it's so critical if you do these follow-up observations. And unfortunately, we often aren't very good at doing that. Okay, so people are always asking me, what's the risk of a potential impact? And basically, it's 100%. Sooner or later, the Earth is going to get hit by an asteroid, and it may be a big one. It's most likely going to be a medium size, or maybe a 50 or 100 meter asteroid, and it's going to cause a lot of damage. So that's going to happen someday. We're always being asked what's the probability for different sized asteroids to hit the Earth. You go out and Google that, or do any kind of research. Different numbers. So it might say, for a 50-meter asteroid impact, those happen every, say, 500 years. And for a 100-meter asteroid impact, those happen every 2,000 years. For a 1-kilometer asteroid impact, that happens every 10 million years. But you'll see different numbers depending on the source that you look at. And that's often a source of frustration for me, especially sometimes when I look at how they arrived at the numbers. They really have kind of stretched their statistics a little bit. And it often seems like the risk probability is kind of a function of how much money somebody is trying to get in the grant. So it can be interesting. So I thought, just for grants, that I would do a little project to kind of do my own assessment of what the risk is. So I did a 1-year study. What I did was I considered a sample space. Thanks for jumping the gun on the slide. I considered a sample space that's centered on the Earth. It's a spherical space with the radius being equal to the distance to the moon. So basically, this is a space through which asteroids occasionally pass, and it's, how close does it get? Well, the question is, how many asteroids get closer to the Earth than the moon? And I did this for 1 year. And during that time, 53 asteroids passed the Earth closer than the Moon that we know. Generally, if they're larger or smaller than 2 meters, we're not going to discover them, so it's probably a much higher number. But these are the ones that we were able to detect, and so I did some statistics on it. So if you want to look at the next slide. Again, we had 53 objects, and this is the distribution of the size. You see that almost all of them were smaller than 30 meters. In fact, 92.5% of them were smaller than 30 meters. The closest approach was 16,260 kilometers, which is more than 1 Earth diameter. So actually didn't come very close at all. The largest of them, there was one that was 62 meters in size. All the rest were smaller. Like I say, more than 90% of them were smaller than 30 meters, which we consider to be the lower limit for being able to survive entry into the Earth's atmosphere. Anything smaller than 30 meters is likely to break up when it enters the Earth's atmosphere. So that part of it makes you kind of feel a little bit better that it's mostly the small stuff that's flying around out there. But then there's one other statistic that I think is kind of interesting. Of the 53 asteroids that we detected coming closer to the Earth than the Moon, 51 of them were discovered within 1 week of closest approach. So that's kind of scary. That means that if one is coming our way, our chances of discovering it in time to do anything about it is pretty small. And that discovery within 1 week, that's plus or minus 1 week. In many cases, we don't discover them until after they've made the close approach and they're on their way back out again. So just some interesting statistics. And, you know, that sort of makes you wonder, should we worry about it or not? So if we go to the next slide. You know, people ask all the time, should I worry? And, you know, these are some of the answers that I give people. First of all, yes, the Earth will get hit someday by an asteroid. We don't know when. We're looking. We're going to try to warn you if it happens. But the reality is, you may get very little, if any, warning about an asteroid impact. And we saw an example of that with the Chelyabinsk impact back in 2013. There was an asteroid that had been discovered a year earlier that we knew was going to make a very close approach to the Earth on Friday, I believe it was the 15th of February 2013. So we were all excited about that. We were watching the skies for that one, and a completely different asteroid snuck up on us. We didn't see it coming. It came from the day side and exploded over Chelyabinsk, Russia, and injured somewhere between 1,500 to 2,000 people, primarily from the shock wave of the asteroid exploding in the sky. That shock wave blew out windows, knocked over some walls, caused a lot of damage. One of the interesting things is people apparently forgot the lessons they learned during the Cold War about what to do when there's a bright flash in the sky. As that asteroid came down, it lit up the sky. It was actually for a few seconds brighter than the sun. And so everybody rushed to the windows to look out and see what was going on. And the asteroid exploded, and several seconds later, the shock wave hit. And everybody standing at the window was suddenly having flying glass hit them in the face. So that's the scenario. That asteroid was somewhere between 17 and 19 meters in size, and we had no warning that it was coming. Sometimes people come up to me and say, well, what's the probability that I'm going to get hurt or killed by an asteroid? And I can point to anyone in this room and tell you with 99.99999% certainty that you won't get hit by an asteroid. It's actually a very rare event. Yeah, it's possible that it could be a very major event, but for any one individual, your chance of being hurt or killed by an asteroid is just about zero. Now, I mentioned a while ago how we're finding these asteroids just very short periods before they make their closest approach. What we would like to do is find them years in advance. If we are able to discover an asteroid, say 10 years before a predicted impact, or even 10 years before a high probability of an impact, we can do something about it. We actually have existing technology today that we could use to deflect the asteroid, prevent that impact. But to do that, we have to be able to discover the asteroid years in advance and determine years in advance that there's a potential impact. And that's frequently not possible with the technology that we're using today. So that's about it. Next slide. If anybody has any questions, I'll be glad to take those questions now. See a couple hands there. Claude, I guess I'm going to have you kind of pick out who's going to be answering what questions.
Sure, and we have a microphone here that we can sort of pass back, except it's a little bit knotted up. Dick, can you speak loudly?
Sure. Well, that's actually. Just wondering what magnitude range your observations are, and are your observations or the other ones that refine these orbits?
That's a good question. As I mentioned, we work in the red part of the spectrum, and typically we are looking at objects that are somewhere between magnitude 18 and magnitude 22. And 22 is about the limit for our telescope at Chabot. However, if you look at the Minor Planet Center listing of observations, there are a number of observatories around the world that can go down to about magnitude 24. And as we find all the big asteroids, and we're looking more and more for the little ones, that becomes a constraint. We're now seeing objects that are so small that they're down in that magnitude 22, 23 range. And that's limiting the number of observatories that contribute to the program. So, if you're thinking of doing this with your 8-inch Schmidt Cassegrain out in your backyard, unless you can go to magnitude 22, you're not going to be able to do much.
The questioner happens to have a 40-inch in his backyard. 30. Oh, excuse me, 30-inch. Okay. 30, excuse me. Inflation.
Oh. Well, you might be able to do it.
Yeah, I could.
What is the logic by which you have become convinced that you've discovered 90% of the 1 kilometer greater?
It's based primarily on the rate at which we're discovering them. As I mentioned, the program to find the 1 kilometer or larger asteroids started in the mid-1990s. It was instigated because of the Shoemaker-Levy 9 impact on Jupiter. When that impact occurred, some of you may remember, images came down showing these huge blotches in the atmosphere of Jupiter that were the size of the Earth. And someone in Congress got hold of that information and said, well, you mean that could happen to the Earth? And that started the whole process. And Congress tasked NASA with finding the 1 kilometer or larger asteroids. Since then, there's been quite an effort to do that. Initially, we were finding a lot of them. The rate at which we were finding them was pretty high. But what's happened is we are finding fewer and fewer new ones. We're still seeing the ones that have already been discovered, but the discoveries of the new ones has gone down quite a bit. We rarely find new 1 kilometer or larger asteroids. And based on that fact, we are concluding that we've likely found most of those 1 kilometer or larger asteroids.
If their albedo was very low, though, it would be very difficult. You're only measuring albedo from the magnitude, so if they have a very low, presumably a long exposure to the rays from the sun, and the equivalent of desert varnish, they've got a low albedo and therefore harder to find.
That's true. And for observatories, especially observatories on the ground, which are relying on reflected sunlight to find these objects, that is a concern. However, there was a program, NEO WISE it was called. It was the WISE spacecraft, which was an infrared telescope spacecraft that was tasked with looking for asteroids in the infrared spectrum. So dark asteroids, even though they don't reflect much visible light, they emit a lot of infrared light. And so that program went on for several years. They also reached the point where they were finding very few asteroids using infrared. So, they covered both the visible, which is reflected light, and infrared, which was emitted energy. And so we're fairly certain that we found more than 90% of it.
How would you say that LSST, the Large Synoptic Survey Telescope, once that comes online and starts covering the, doing their all-sky survey, every few days, how will that change the equation as far as NEO discovery and being able to cover down to smaller objects, like you're saying, down to the 140-meter class range?
Well, that's a good question. We're thinking we're going to get flooded with data once LSST comes online. So they're going to be able to see objects potentially down to magnitude 25 or 26. And we expect to have quite a flood of data at that point. The Minor Planet Center has already been asked by NASA, what is your capacity to handle that? And the guys at the Minor Planet Center, all 8 of them, have assured NASA that they can handle the flood of data that's going to come from LSST when it comes online.
Chabot is not known as a incredibly dark site, shall we say. How do you deal with the light pollution that you have in the area? I assume partly reasonably short integrations, and you already said that you observe in the red. How else do you mitigate the light pollution of East Oakland?
I cuss at it a lot.
Oh, don't do that to me.
That's actually becoming a serious problem, especially in the last few years. The city of Oakland and other cities in the Bay Area have converted over to these LED street lights, and it has made a significant impact on light pollution. A while ago I said we were getting down to magnitude 22. I think today we would actually have trouble getting down to magnitude 22. But a couple of things we do, rather than taking one long image, we take a bunch of short images and then stack those together. We have to do that for asteroids that are moving more than about, I'd say, 1 arc second per minute of time. We have to use what we call stack and track. But even for asteroids moving slower than that, we tend to use that technique rather than trying to take longer exposures. It's just a better way of doing it and getting data. But sometimes I have people sit and watch over my shoulder when I'm doing this, and I spot asteroids in an image, and they can't see it. So part of it is just getting the skill to spot it. You know, I'll look at an image and I'll say, oh, there's an asteroid right there, and they're looking at it and I say, where? And there's this little faint, fuzzy little thing there that's to spot. So it's a challenge, and light pollution is definitely an issue.
Any other questions?
Is that you?
Well,
I've got another one.
of course, Byron.
If we were to possibly have a couple weeks' notice and try to intercept and explode one, I would think the correlation between the Tholen categorization, which really relies heavily on shape, if that was correlated with whether it was a stony or an iron, might be relevant to the whole issue. Has any work been done on that, correlating Tholen with meteorite categories? You mentioned it already somewhat, but is there any success on that?
Yeah, I'm not sure. You said if we discovered it in a couple of weeks, that wouldn't be enough time to do much other than warn people to get out of the way. We would need years in order to actually go up and try to mitigate and redirect an asteroid. As far as matching the Tholen classification, there's also another classification called the Benzel classification, and I think there's one or two others. There have been some attempts to try to match those with meteorites that we find on the ground, and there's been a fair amount of success in doing that. It turns out that, for example, a lot of meteorites that we find on the ground come from Vesta. And there are quite a few asteroids that are near-Earth asteroids that it turns out also match the spectroscopic signature of Vesta. So yes, there has been some effort to categorize and match the classification of the asteroid to the meteorites that we find on the ground.
Anything else?
Yeah, a couple of questions. So in terms of the discovery rate of new asteroids, let's say in a certain size category, I guess you've got asteroids coming in from further out, right? If I'm not mistaken, from further out in the solar system that we may only see once every so many hundreds of years. So do you have any idea what the how many of those are coming into the inner solar system over a given year, let's say?
Well, we discover about 1,000 new near-Earth asteroids every year. And as far as the asteroids out in the main asteroid belt or farther out, I couldn't give you a number off the top of my head. I don't really track that part of it. But I do know that there are quite a few that get discovered every year in the main asteroid belt. Also some that are farther out in the region of Jupiter and beyond. And then, of course, there are comets that come in from the Kuiper Belt or the Oort cloud. And I don't do comet work, so I can't give you the numbers, but I know there are quite a few that show up every year. I do get emails from the Minor Planet Center whenever they designated a new comet. And I'd say I get 3 or 4 of those a week. So, those objects are out there. And then, of course, we recently had an asteroid that turned out not to be from our solar system. I don't know if you folks are familiar with that. Asteroid Oumuamua is an interstellar asteroid that shipped up in October of last year. And that was pretty exciting. Had all the guys globally, just everybody was out running to their telescopes wanting to observe it and track it. Especially initially, nobody believed that it had an eccentricity greater than 1. They said, that can't be. So they were literally discarding data that was actually valid data.
And one other question, a very basic question. Can you explain why asteroids tend to be biased more toward the red end of the spectrum in terms of their emissions?
Primarily because of space weathering and the composition of the asteroid. Space weathering actually tends to cause the asteroid to have a slightly reddish hue. If you looked at it, it would look black, but or dark gray. But in reality, it's got a red component to it. So space weathering, also the composition, especially things like carbonaceous asteroids that have a fair amount of organics to them. So it's just turns out to be a characteristic of asteroids that they tend to be a little bit brighter. Not always, but most of the time they're a little bit brighter red parts.
Anything else? Well, join me in thanking our speaker one more time this evening. Gerald, thank you so much. We really truly appreciate this. And anytime you're down in the Big Bear area, look us up. Either the club, you know the president here, sitting next to me, and or of course here at the...
And I see the president's wife over there in the corner.
Oh, it's the president.
No, the
Hi,
president.
Teresa, how are you?
Pretty good, yourself?
Right? Are you sick too, or is it just clogged?
No, I've got it too.
We came down with it in unison.
Yeah.
It was, we just came back from that cruise, and it was not a fun trip home. Anyway, thank you so much. We'll let you go, and we'll talk to you again some other time.
All right.
Thank
Talk to
you.
you later.
Thank you.